A photon leaves the sun. 8 minutes later, by your clock, by every clock on Earth, by every clock in the solar system, it arrives at your eye. You experience it as light, warmth, a sunny afternoon. Now here's the question nobody asks. What did the photon experience? The answer is nothing. Not almost nothing. Not a very short duration. Zero. From the photon's geometric perspective, in the only mathematically precise sense we can give to that phrase, the moment it was emitted and the moment it hit your retina are the same moment. No time passed. No journey occurred. The 8 minutes existed for you, not for the light. I'm Paul Dirac. This isn't a poetic metaphor. It's what special relativity actually says. And if you follow it carefully, it doesn't just tell you something strange about photons. It tells you something strange about time itself, about what time is, whose time it is, and whether the flowing present you experience is as fundamental as it feels. Let's build this from the ground up. Time dilation. You've probably heard the phrase. Let me tell you what it actually means, physically, experimentally, not metaphorically. When objects move, their clocks run slow. Not their mechanical clocks, all clocks. Every physical process that constitutes a clock, atomic oscillations, radioactive decay, heartbeats, the chemical reactions of metabolism, all of it unfolds more slowly for a moving object than for a stationary one. This is not an illusion. It's not a measurement artifact. It's a real difference in the rate at which time passes. The evidence is overwhelming and direct. Atomic clocks, the most precise timekeepers humans have built, have been flown on aircraft and compared to identical clocks left on the ground. The clocks that flew tick slower, by exactly the amount special relativity predicts. GPS satellites orbit at high speed and at altitude, both of which affect time rates, relativistic and gravitational effects both, and the GPS system must correct for these effects continuously. Without the correction, navigation errors would accumulate at roughly 10 kilometers per day. The corrections are not optional engineering choices. They're required by reality. And then there are muons, unstable particles created when cosmic rays strike the upper atmosphere about 15 kilometers above Earth's surface. Muons decay. They have a half-life of about 2.2 microseconds at rest. At the speeds they travel, close to the speed of light, they should decay long before reaching the ground. By naive calculation, they shouldn't make it more than a few hundred meters, but they do reach the ground, abundantly, because from our perspective, time is running slowly for them. Their half-life, in our frame, is stretched by the Lorentz factor. They survive far longer than a stationary muon would. This is not theory, it's measured. Muon time dilation is one of the most direct experimental confirmations of special relativity. So, motion through space slows the passage of time. The faster you move through space, the slower you move through time. This trade-off is precise, quantitative, and real. Now, how much slower? There's a factor, the Lorentz factor, gamma. It depends on velocity relative to the speed of light. At everyday speeds, gamma is essentially 1, no measurable dilation. At 87% of the speed of light, gamma is 2. Your clock runs at half the rate of a stationary clock. At 99% of C, gamma is about 7. At 99.9%, about 22. The factor grows steeply. The pattern is clear. As you approach the speed of light, the time dilation factor approaches infinity. A clock moving at exactly the speed of light would show zero elapsed time for any journey, regardless of how long that journey takes by any external clock. For a photon moving at exactly c, the mathematics gives exactly zero proper time, not approximately zero, not some very small number, zero. Whatever spatial distance it crosses, whatever coordinate time elapses in external frames, the proper time, the time experienced by the traveller, is zero. But here I want to be careful, because there's a subtlety that matters. In special relativity, time dilation is properly understood by transforming between reference frames, the frame of the stationary observer, the frame of the moving traveller. You can always ask, what does the moving observer's clock read? You can always boost to the traveller's rest frame. This works for anything with mass. For a photon, it breaks down. You cannot define a rest frame for a photon. In every inertial frame, light moves at c. There is no frame in which the photon is at rest. The concept of the photon's perspective as a reference frame is not defined within special relativity. So when we say the photon experiences zero time, we're being precise in a different way. The proper time along the photon's world line, its path through space-time, is zero. This is a geometric fact, not a statement about perception. It means the space-time interval between the emission event and the absorption event, measured along the photon's path, is exactly zero. Not just small, zero. Let me explain what that means geometrically, because this is where the real insight lives. In special relativity, we don't have space and time separately. We have space-time, a four-dimensional structure where space and time are dimensions of the same thing. The distance between two events in space-time, the space-time interval, is calculated differently from ordinary distance. For events connected by a massive particle's world line, the interval is real and positive. It equals the proper time experienced by that particle. For a photon, for anything traveling at exactly c, the space-time interval is zero, always, exactly. This is what physicists call a null geodesic, a path through space-time with zero length. The photon traces a null geodesic from its point of emission to its point of absorption. Those two events, despite being separated by 150 million kilometers of space and 8 minutes of coordinate time, have zero space-time separation. The photon doesn't travel between two well-separated events. In the geometry of space-time, those events are right next to each other. Space stretched between them. Time elapsed between them for observers. For the geometry of the photon's path, nothing. Now scale this up, because the cosmological implications are something. The Andromeda galaxy is 2.5 million light-years away. The light reaching your eye tonight left there 2.5 million years ago, before our species existed, before the earliest stone tools, before the genus Homo had appeared. That light crossed intergalactic space for 2.5 million years. The stars it passed, if any, aged. Galaxies evolved. On Earth, everything changed. And the photon? Proper time, zero. For that photon, emission and absorption are not separated by 2.5 million years. They're not separated at all. The star that released it and your eye that received it are, in the photon's null geometry, the same event. The entire journey, from the photon's geometric perspective, has zero duration. Go further. The cosmic microwave background, light released 380,000 years after the Big Bang, now reaching us after traveling for 13.8 billion years. Each of those photons, zero proper time. They've been crossing the universe for longer than Earth has existed, longer than the Sun has existed. For them, in the only sense special relativity permits us to say, the Big Bang and your kitchen are the same moment. Every photon ever absorbed was absorbed at the same moment it was emitted. In the null geometry of light, there are no journeys, only connections. This forces a deeper question about time itself. We're taught, intuitively, that time is a universal backdrop, a clock ticking everywhere the same, a now that applies to the whole universe simultaneously. Special relativity removes this completely. There is no universal now, there is no cosmic clock. Time is something that accumulates for objects moving through space-time, and it accumulates at a rate that depends entirely on that object's trajectory. Two observers moving differently through the same region of space-time will accumulate different amounts of proper time between the same two events. Both amounts are correct. Neither is really right. Time is local, personal, trajectory dependent. Massive objects, you, me, muons, GPS satellites, stars, always accumulate some proper time. We always experience duration. We always age. The minimum is zero, approached asymptotically as speed approaches c, but never reached by anything with mass. A photon is different in kind, not just in degree. It travels at exactly c, it accumulates exactly zero proper time, it doesn't experience duration, asymptotically reduced to near nothing, it genuinely has none. Your now is a real thing, local to you, defined by your trajectory. The photon has no now. It participates in time only from the outside, as seen by the observers at its endpoints. From within, if within even applies, there is nothing. Not darkness, not a flash, not an instant. Just the null geometry of a path that, in space-time, has no length. And here's where I want to be honest about the boundary of what physics tells us. We can calculate the photon's proper time with complete precision. Zero. We can describe the null geodesic geometrically with full mathematical rigor. We can verify time dilation experimentally to extraordinary precision. What we cannot tell you is what it's like, if anything, to be a photon. Does zero proper time mean the photon exists in an eternal instant? Or that it doesn't experience anything at all? Or that the question itself, what does a photon experience, is simply not a well-posed question, a category error, like asking what color jealousy is? I don't know. Physics doesn't answer this. Physics describes physical processes, geometric structures, measurable quantities, transformation rules. It doesn't address the subjective dimension of existence, and it's not clear it ever will. Whether photons have any form of inner existence is a question that may permanently lie beyond what equations can reach. But this much is true and verifiable. Something can exist in space-time, can connect two events across any distance, any span of coordinate time, without accumulating any proper time at all, without aging, without duration, without, in any geometric sense, having a journey at all. And you, made of particles that accumulate proper time, that age, that have trajectories through space-time with real length, you perceive time as flowing, as having direction, as something you move through, inevitably, irreversibly. That experience of time passing is the most intimate fact of consciousness, and yet it's not a universal feature of physics. It's a feature of massive objects on time-like trajectories. The photon doesn't share it. The light that warmed your face this afternoon left the sun without knowing it was leaving, arrived without knowing it was arriving, crossed 150 million kilometers of space and 8 minutes of your time in what for it was no time at all. What does that tell you about your 8 minutes? What does it tell you about time? I've been thinking about it for a long time, and I still find it genuinely strange.